Okay, in this video, I would like to start a series on beam theories and explain the content for each theory and their differences, and more importantly, maybe answer the big question, why do we need so many or several beam theories? But in this first video, I would like to establish a foundation with some introduction. The content is as listed here. Um, First, I will go a quick introduction to the index notation. I will use index notation throughout, mostly at least, and then a map for kinematics to kinetics related to any continuum media, but specifically to apply to beam theories in future videos. And that would be basically explaining how do we go from a displacement field to equilibrium, and also explaining the requirement or the condition that the Saint-Venant's compatibility applies to, or as a condition for compatibility we use Saint-Venant equation. Okay, so let's start here with uh, okay, let's start with the index notation. Index notation is useful because it is more compact. It's alternative way of expressing scalars like vectors and tensors in a more compact way. For example, if you have a vector, let's say A in general, usually designate this with an arrow or sometimes a boldface letter like this. And this has three components in the three-dimensional space. Rather, we come here and say AI as an index, and I goes from 1, 2, and 3. So basically, when I say AI, I am showing a vector which has components A1, A2, and A3. And when I say A1, A2, A3, I mean the components on a three-dimensional space, and we usually sometimes call them 1, 2, 3, similar to X, Y, Z. Now, if I have an expression which has a repeated index, let's say, for example, AI, EI, these are two vectors, I should sum up on these repeated index. This is the rules for index notation. So basically, I can have A1, B1 plus A2, B2 plus A3, B3. Actually, this is a very nice way of saying that this is equivalent to A dot B. The inner product of two vectors uh, can be represented in index notation like this. These are for repeated indices. But if you have a free index, for example, you have AI, say J, which is a tensor, for example. So this tensor is two free indexes. So it would be A1, 1, A1, 2, A1, 3, and so on. Similarly, if you say AI is, actually I should put transpose here as I showed it here. Now, if you have an expression that contains comma, let's say AI comma J, means this comma means differentiation or derivatives. So here we are saying that we are taking the derivatives AI with respect to xj, for example. This is a tensor by itself. So these are some. In addition to that, there are two that I will introduce as I will go through it, canonical delta and permutation symbol. But this is very brief introduction to tensor notation in terms of index notation, and we will use it throughout the video. Now, one thing that I would like to map here, and I will follow this throughout all the videos, is that if you have the displacement field, let's say you have, I will write it uh, in simple language here without using notation now. Displacement, you can calculate from this displacement the strain field. And from strain field using constitutive, so from here to have, we have a relationship that we can use. From strain, we can go to stress using a constitutive relation, a material type of behavior. And from stress, we can go to equilibrium, which is the relationship between the components of the stress. Now, usually in practice, we have the applied forces. Let's say if you have a beam with any boundary condition, you have some load on it, and then you have the applied load, and then you apply the equilibrium equation, and then kind of, if I use maybe a different color here, um, you go backward. So from equilibrium, you get the stresses, you may want to get the strain, and you end up with displacement. So let's say here you want to see how much deflection you have, or how much shear stress or bending stress you have, and or forces, and so on and so forth. So in practice, we go backward, but there is a catch here. In this part, when we go from equilibrium to stress, not all the strain field can give you a compatible displacement field. And that is where St. Venant comes in. And St. Venant is a condition that guarantees that we have from our strain field, if we get to the displacement field, we have a compatible displacement field. If this condition is not satisfied, this displacement field may be it's like in a medium, like say in a plate or in a beam or any medium that we are considering, could be an overlap or could be a crack. Not crack due to stresses, but crack in terms of kinematic. There would be disjoint in certain areas. But this St. Venant guarantees that we don't have that. Okay, so using this map, which is a very brief and safe way approach in any continuum mechanics, but here I will focus on beam theories, and we will use this map to arrive at different beam theories and explain each one and move forward. But let's start with giving it some mathematics and some notation. Okay, so let's assume that we have a displacement field ui with the component, say u1, u2, u3. This is equivalent to say that we have ux, x component, uy, y component, and uz, z component. Each component could be a function of space, x, y, z, but in general we have this. So I will not repeat any vector notation based on the explanation that I gave you here. So I will fully stick to index notation, but here and there maybe we use the equivalent tensor and in terms of vector notation. So another thing that it's good to have, if you have an expression that has only one free index, that is a vector. And if you have two free index, that is a tensor of second rank. Actually, all of the quantities we can say it is a tensor, but if it is one component, so it is 3 to power 1 free index, 3 to power 1, 3 components. If it is two free indices, then you have 3 to power 2, 9 components, which is a tensor, and so on. And you can expand this way, these to, any dimensional space, but in physical world, we are working in three-dimensional space. Okay. So from here, what I will do, I will go to, I want my strain. And we know that strain is a tensor, like say EIJ. So it has 9 components. This strain tensor can be calculated using the relationship between displacement field and actually their derivatives. And so this is the, from here we can calculate, if you give me this u displacement field, I can calculate the strain field. As you see, I have two free indices, and therefore EIJ would be a three-dimensional space would be E11, E12, E13, E21, E22, E33, E31, E32, and E33. So these are normal strains, and the off diagonal is the shear strength, sorry, shear strength, and then you can see. So to be clear here, when I say E12, I mean tau xy, and so on. So I can simply calculate here, and as I mentioned here, actually this is ui dxj, and this is duj dxi, and I and j goes from 1 to 3. Okay, so having that, so basically coming back to our map, is we have the strain, and this is fully consistent because you have the displacement for a admissible and acceptable displacement field will give you a acceptable and admissible strain field. Now, how do we go from strain field to stress field? So we need a constitutive equation. This comes, uh, this is basically a material behavior, and the way or the rate could be also the load applied to the material. It, it could be many things that we have. And then basically here we have a mathematical model that describes the behavior of our material uh, in relation to its kinematics. One thing here, I should say here that uh, so far here, maybe I use another color here. So far I have been using displacement and strain. So this part is kinematics. Okay, as I explained here. But now we want to arrive at the kinetics. When we talk about force and stress, we arrive at the zone of kinetics. Okay, so in beams and in solids, what we use is actually the, call it sigma ij, which is the stress. Immediately you should notice that sigma ij has two free indices, so it has 9 components in three-dimensional space. Is given by this relationship that has a lambda delta ij, and I explain what delta ij stands for. EKK, these are indices, plus 2 mu EIJ. Now, one by one, lambda and mu are Lamé's constant. It could be a function of space, it could be a function of temperature, but usually we take them as constant. This mu here is basically the shear modulus of elasticity. Now, delta ij is 1 if I equal to j, is 0 if I is not equal to j. And this is called Kronecker delta. It has the property. So if you have delta 1, 1, it is 1. If you have delta 1, 2, it's 0. EKK, what is EKK? Actually, I have already explained this in terms of the notation, I mean. You have two repeated indices, so it should sum up. So it is E11 plus E22 plus E33. And if you go back to the strain tensor, it's basically the trace of this strain tensor, or the summation of the diagonal. It's a kind of volumetric strain that we have here. It's a kind of bulk strain of the material, and then proportional. And this piece is the shear stress part. Okay, so once I do that, then I can also explicitly mention that this has sigma 1, 1, sigma 1, 2, sigma 1, 3, sigma 2, 1, sigma 2, 2, sigma 2, 3, sigma 3, 1, sigma 3, 2, and sigma 3, 3 in three-dimensional space. 9 components. So if you recall, or if you like, you can actually show this. I maybe this will not be a maybe I should get a nice sketch maybe for the next video. So if this is your, say, x or 1, maybe put x here, y here, or maybe actually let's do it correctly. So x, say y, and z, for example, here 1, 2, 3. So sigma 1, 1, which is sigma xx, is the stress which is normal to the face, which is normal to x-axis and in the direction of x-axis. Sigma 1, 2 is again on stress on that the same face, but in the direction of y, and sigma 1, 3 is the shear stress on the same face in the direction of the z. So this is 1, this is 2, this is 3 coordinates axis. And then I will not draw the rest of them, but you can do the same. I mean, I will probably find a sketch that shows this more clearly, but the concept is clear here, what we are doing. Okay, so now what? Well, as you see here, if I follow my overall map, displacement strain, I have got my strain from my displacement field, and I got my stress from my strain. Uh, so now I have my stresses. What can I do now? Well, these stresses will satisfy or should satisfy the equilibrium equation. Uh, also I will not talk about the boundary condition, but of course, considering the boundary condition, it will be a specific solution to that equilibrium equation. And therefore, we go after equilibrium equilibrium equations. So what we have in index notation, you come here and say the the stresses that we calculate, the divergence of this stress, because J and J, this is the divergence of stress, plus any body force, say car I, should be equal to 0. So this is a very compact form of equilibrium equation. How many equation do we have here? Three, for three-dimensional. For example, I will expand this to see. So let's say I is 1, for example, x component of the equilibrium equation. So this is 1, and j should be summed up because it is repeated index. 1, 1 plus sigma 1, 2, 2 plus sigma 1, 3, 3 plus car 1 equal to 0. But what is this? This is the divergence of this component, and you sum up the everything here, right? So you sum up everything here. If I write it, so this is the divergence of those components on this face that I just showed you. And that is, we know that the divergence should be balanced by the body force. So this is the body force and surface forces that we have. Okay, so this is good. So we arrive at this, and then basically we are done. But as I mentioned, in practice, usually we have the equilibrium equation with, according to applied laws. We calculate the stress, we come at the strain, and we would like to come up at displacement. But there's a catch here. And the catch is that if you arrive from a given strain field to your displacement field, it there should be a condition satisfied, and that condition is Saint Bernard, to make sure that this is unique for that strain field. So in other words, you don't have any physical gap or physical overlap in your domain. So Saint Venant was the scientist that worked on this Saint Venant's condition. This guarantees that from if you come from strain to UI, then this condition should be satisfied. And this is in a very abstract way is given as an equation which is EIJ comma KL. This is double derivative plus, these are partial of course, IJ minus EIK JL minus EJL comma IK equal to 0, or we can make it more compact, writing it as IPR epsilon JQS and EPQRS equal to 0. In here, these epsilon are called permutation symbols. They are not stress, they are not kind of tensor, they are symbols. And the property is that if indices repeated is equal to 0, else is either +1 or -1. For example, epsilon 1, 1, 2 is 0. Epsilon 1, 2, 3 is 1. Epsilon 3, 2, 1 is -1. And the rule to do this is, so if you draw 1, 2, 3, in this direction, the clockwise direction gives you +1 if your indices are this, and counterclockwise gives you -1. So you see here is 3, 2, 1, it gives you -1. But 1, 2, 3 is +1. 3, 1, 2 is 1. 3, 2, 3, 1 is 1, and so on. If you have higher dimension, so if you have, I don't know, 10 indices, there is another rule that um, well, there's a guideline actually to give you the this value, but this is the property, and then you can write it. Okay, so I guess that's good for this introduction. So we are going to use this map for beam theories, and I hope this you find this introduction useful. Of course, you need some um, prerequisites in terms of the continuum mechanics, or in general elasticity and index notation, but I try to summarize it here based on this map for our usage for future videos. Thank you.